All right, on to page 3, I guess. That was the front and back of page 1. Here we go on to the next page, page 3 and 4. All right, the foundation of your house has about 1,200 termites. Well, that's great. The population doubles every 15 days. Okay, I know during exponential functions, people are always like, when do I use population doubling or halftime? The answer is, it says the population doubles. This is a doubling problem. So instantly we know we are having population equals P naught times 2 to the power of the number of years that pass, or like how long passes divided by the length of the doubling period. So we need to pick out these informations. This information. So it started with 1200. So remember, that little naught always means at time 0, at the start. So that is our initial condition. Or we can look at this formula here. It's the a value in y equals a times b to the x. The number in front of the exponent is always the starting condition. Okay, so it doubles every 15 days. So our doubling time is 15 days. And I'm going to write days because the time and the doubling time have to have the same units. Otherwise, you get absolute nonsense. Then it says, how many will there be in a year? So my time is 1 year, but that is not days. So we can't use this. We've got to switch this over to days. So there's 365 days in a year. And now I can substitute everything into my formula. And I will get P naught, 1200. It's a doubling problem. So my base is 2. We could report the base if we wanted to as well. The time is 365 days. And the doubling time is 15 days. You can work that through on your calculator. You can either work out the 365 over 15. And remember, this is an exponent. This is not a fraction. It might kind of sit a little low on this one because I didn't want to write it too small. Ooh, I'll do that. Yeah, we'll just leave it alone. But that is an exponent. So it's going to be 1,200 times 2 to the power of, and if you're doing it on your calculator, you might want to put brackets around that. Otherwise, it probably won't work properly for you. And my calculator gave me this number, 2.54 times 10 to the power of 10. Scientific notation again. This just means multiply by 10 10 times. And multiplying by 10 means moving the decimal 1 spot to the right. If I multiply by 10, I would just move it there, and I'd have 25.4. So I'm going to do that 10 times. 1, 2, and then I'm going to have 8 more spots. So I'm going to have 8 zeros. So it's going to be 2, 5, 4, and then 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So something like that. So therefore, we're going to have 25.4 thousand million billion termites after 1 year. Ugh. Okay. Doubling time, easy, as long as you recognize it's doubling time. If a town's population is currently 50,000 and it decreases by 2.5% every year, so this is decay. But I can't assume it's half-life. Nothing is said it gets cut in half every year. I'm just given a rate of decay. So what will its population be in 25 years? So if it's decay, growth or decay, but it's not doubling or not half-life, that means it is just a normal exponential. Y is equal to a times b to the x. So let's pick out what it is. So it starts at 50,000. That's our A value. That's the number in front of the base. Then it decreases by 2.5% every year. This is like depreciation. So this means we need to do 100 minus 2.5 to get our decay rate, and that will give us 97.5%, or 0.975. So B is 0.975, and then our time is 25 years, so the number of times we're doing this is 25. Then we just substitute in 50,000 times 0.975 to the power of 25. And this is the power of exponential, of compounding ideas, right? Like, it's only going down 2.5%. So how much could it really go down after 25 years? Well, in reality, it's going to drop to 26,551 people. So it's almost been cut in half by only dropping 2.5% every year. Okay, next. The value of a new pair of iPods depreciates. So that tells us this is another decay problem, but not half-life. It doesn't say half-life, just decay. So we are going to have y is equal to a times b to the x again. So let's find what they are. It goes down 13% per year. 100 minus 13 is 87%. So our b value is 0.87. If you bought your AirPods for $229, that's how much they were initially. That's our starting condition. And then 5 years later. So we'll plug those in to our equation. And when we calculate that out, we will get $101.61. So after only 5 years, they're worth less than half of what you paid for it. And we'll do our therefore statement and everything else. So yeah, we did 100% minus 13% equals 87%. That was how we got our B value. Okay. British Columbia's population, P in millions, can be modeled by the equation right here. So it gives us the whole equation. So this is an exponential. Where T is the number of years since 1983. So if that's an exponential, we know immediately A is 2.9 in millions, so 2.9 million, because whatever number is in front of our growth decay factor, the exponential, the power, that's our A value. Whatever is the base is our B value. B is going to be, well, here we have to think the other way around. So we're multiplying by like 1.0257. So that means, so that's 102.57%. So really, we're growing by 2.57% every year, right? 100 is just staying where we were. So we're growing by 2.57% every year. And then we don't know anything about T because we don't know what year we're talking about yet. So what was the population in 1983? 1983 was when this started. So how much was it at the beginning? That's our initial condition. That's our A value. 2.9 million people. What percent has it been growing? Well, it's been growing by 2.57% each year. If you forget this little bit here and you get like a 102.57%, you'll get the majority of the mark. What do we expect the population to be this year in 2025? Well, we start with the formula. P is equal to 2.9 million times 1.0257 to the power of t. T is the number of years since 1983. So in this case, t is going to be 2025 minus 1983, the current year minus that year. See how much time has passed, which I think is probably about, well, what's that come to, 42 years. So that'll be 42. And then you just plug it into your calculator. And I get 8.4, but we know that population is in millions, so this is 8.4 million people. That's a lot of people. But I feel like at this point in time, British Columbia's population might be higher than that. Have to look that up later. Moving on. All right, we've got parabolas. So we've got lots of different versions of what a parabola looks like. In this one, we are looking at vertex form. Y is equal to a times x minus h squared plus k. And we need to understand what all of these do. That's what this question is asking. So a, that modifies our step pattern. So our normal step pattern, 1, 3, 5, 7, and so on, is how much a parabola goes up every time we go over 1, left or right, because it's symmetrical. If a is a number bigger than 1, then it'll grow faster. It's going to stretch it vertically. If it's a number less than 1, it's going to compress it vertically, which is going to make it look wider. And if a is negative, it's going to flip it upside down. So normally a parabola opens like that. If a is negative, it's going to open like that instead, right? And then when it comes to h and k are the vertex. So the vertex of our parabola is the point hk. Whether it opens up or down, it doesn't matter. That's our vertex. The one thing we have to watch out for is that this is minus h. So we have to switch the sign. For k, it's plus k, so we do not switch the sign. But for minus h, we have to switch the sign. Okay. Let's do the first one. Y is equal to x minus 5 squared minus 8. So we've got h is 5. It's x minus 5. I have to switch the sign. I just take that part. K, I do not switch the sign, so it's negative 8. And a would be right there. There's nothing there, but it's multiplying, so that means it would have to be a 1. So a is equal to 1. So the vertex is hk. H is 5. K is negative 8. So that's where the vertex will be. 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5, 6, 7, 8. There is my vertex for this one. And my step pattern will be the 1, 3, 5, 7 multiplied by a, which is 1. So it's just going to be 1, 3. We normally just write the first 3. So what does that mean? From the vertex, I'm going to go right 1 up the step pattern. So right 1 up 1, right 1 up 1, then right 1 up 1, 2, 3, then right 1 up 1, 2, 3, 4, 5. I do the same to the left from the vertex. Left 1 up 1, left 1 up 1, 2, 3, left 1 up 1, 2, 3, 4, 5. And then we just draw our parabola through that and label. This is y is equal to x minus 5 squared minus 8. So if you weren't sure how to do that, and I showed you that one, I'd pause the video, try the next couple, and then come back to take them up. For the second one, here is my h. So -2, I've got to switch the sign. Here's my k. 5, I don't switch the sign. My step pattern would be 1, 3, 5, but my a is a 0.5, so it's going to be 1 divided by 0.5, or 1 times 0.5 is 0.5. 3 times 0.5 is 1.5. 5 times 0.5 is 2.5. So there's my step pattern for this one. So we'll find the vertex. We'll go -1, -2, up 1, 2, 3, 4, 5. There's my vertex. Step pattern, I go over 1, up a half, over 1, up 1 and a half, over 1, up 1, 2 and a half. And then I do the same on the other side. And draw my parabola through the dots and label y is equal to 0.5 times x plus 2 squared plus 5. Last one. We've got h is -6 because I have to switch the sign. K is -1. My step pattern, multiply by 2, well, -2. So -1 becomes -2. -3, or 3 times -2 is -6. 5 times -2 is -10. And because they're negative, that means it's going to be upside down. So let's find our starting point. 1, 2, 3, 4, 5, 6, -1. There's my vertex. Then I'm going to go over 1, down 2. Over 1, down 1, 2, 3, 4, 5, 6. And if I had room, I'd go over 1, down 10, but it's not going to fit. Then I do the same on the other side. Draw my parabola. And label y is equal to -2 x plus 6 squared minus 1. That's all there is to it. Now we've got one where you're expected to understand how all these points factor into things. So we've got a graph. This graph is examining the path of a firework that has this equation here. So h is the height above the ground. So my y-axis, because that's normally y, is going to be h, how high it is off the ground. So obviously, nothing below 0 means anything, because you can't be in the ground. The firework won't go into the ground, presumably. And t is the time in seconds, and t is where x would normally be. So that means this is our, our t. Time is going to be horizontally. And since time before 0 doesn't make any sense, the part of the graph over there is kind of meaningless too. So we're only really dealing with the parts where h is positive and t is positive. So how long will it take the firework to reach its maximum height? Now maximum means vertex. So does minimum, but it depends on which way the graph opens. So where's the vertex of this graph? It's right at the very highest point. So that's my x value and my y value, or in the context of this question, this is my time and this is my height. So how long will it take to reach its maximum height? Well, that's the time at the vertex. So it will take 2, time is in seconds, 2 seconds. What is the maximum height? Well, that's the h part of the vertex. That is 169.6 meters. I'm not writing, time and height, but you probably should to make sure your answers make sense. But that's how we solve it. If a firework stays lit for 5 seconds, will it still be lit when it hits the ground? Well, time is the x-axis. Where's 5? 5 is right there. We go up. Well, our height is still above the ground. So, no, it will not. it'll still be like 125 meters above the ground when it goes out, which is good. You do not want fireworks to be lit when they hit the ground. So that's why some of the modeling like this can have value in the real world, right? Fireworks should go out before they hit the ground. And from what height was the firework launched? Well, that would be time 0, right? How high was it at time 0? That's when it's right on the y-axis, or the h-axis in this case. And we can see the value right there. It was 150 meters above the ground before it was launched, presumably off the top of some building or something like that. That's it. And if it said something about how long will it take to hit the ground, well, then we'd just have to find the x value here, right? The t value. And that would be it right there. So this firework would be airborne for 7.883 seconds, and then it would hit the ground. All right, last one for this video. X-intercepts. X-intercepts are also known as the roots. And they are these, like on the question above, where the parabola touches the x-axis. That's a root, that's an x-intercept. And you'll see that's when y is equal to 0, because this is the x-axis. And on the x-axis, y is equal to 0. So essentially, we need to find the values that make that or that 0. Another way to think about it is this is factored form, which looks like this. Y is equal to a times x minus r times x minus s. And in this form, the roots, the intercepts, are these two values, the r and the s. But just like in our graphing before, since they have negatives in the brackets, you have to switch the sign. So it's the same idea. If you use this over here, this will tell you that x has got to be equal to -1 and +5, because we switch the signs. Or you can do x plus 1 is equal to 0, and then you've got to subtract 1 from both sides, so x is equal to -1, and x minus 5 is equal to 0, so you have to add 5 to both sides, and x is equal to 5, and those are your roots. So you either just switch the signs, or you set each of the brackets equal to 0 and solve for what x would have to be. Whichever one makes your brain the happiest, go with that. And that'll be it for our second video. I'll be back with the next page in just a minute.